Hi Year 11, this is Mr. Lim here again, and this is our 8th video on hydrocarbons about benzene. Let's get started. Alright, this is learning intentions. We're just going to be talking about the unique structure of benzene and why it's so special, and then how to name it. Okay, so let's have a look. A special hydrocarbon functional group called benzene ring is a common structure in many organic molecules, okay, and any hydrocarbon or organic molecule with a benzene ring is called an aromatic hydrocarbon or organic molecule. Okay, so this concept of this word aromatic just means that it's got a benzene ring in it. Okay, it can also be referred to a phenol group. Benzene ring is composed of 6 carbons and its ring structure, okay, where each bond between the carbon is a hybrid of a single and a double bond. So it's pretty special, so let's go through. It's different because generally single bonds are longer than double bonds, right? But the carbon-to-carbon bonds in benzene rings are somewhere between the two lengths. So a single bond would be this long, a double bond would be this long, a benzene ring bond is somewhere in between the two, all right? So because it's somewhere in between the two, they're actually all equal sized. So if you think about if you look at the structure of the benzene ring, you could theoretically think of it as alternating single and double bonds. Oops. Okay, that's the diagram at the beginning of the video. How many are there? 5, 6. Ooh, how have I done that wrong? Oops, that's why. There we go. All right, so if you had that structure and they were different lengths, right, this wouldn't be a perfectly regular hexagon. It would be slightly odd shaped because each side is a different length, right? But because they're all the same length, somewhere between a single and a double bond, that is a perfect hexagon or a regular hexagon. It also has a couple of other special properties as well. So let's have a look. Each carbon is single bonded to another substance, usually a hydrogen, but side chains or halogens can also be bonded to the carbon ring. So effectively what that's saying is that, okay, each carbon currently, as I've drawn it, has 3 covalent bonds, so they would be able to have one more substance bonded to it. So this is a benzene ring by itself, okay, with 1 hydrogen going off each of the carbons, right? So it's single bonded to another substance. That's what it means there. All right. So within the carbon rings, there are 6 delocalized electrons. So this is the idea behind why these structures are, why these bonds are different to single and double bonds. So in a single double bond structure here, you would expect these electrons to not move around, but what actually happens is that these electrons here, the ones that would make up the double bonds, those electrons can actually move through the ring, okay? So they move around in random directions around the ring, and therefore they are delocalized. So there are 6 electrons, 1 for each carbon, that move around that ring and are delocalized from the other electrons, all right, or compared to the other electrons. So there are 6 delocalized electrons, 1 from each carbon, which move around the ring, but not between molecules. So similar to buckyballs or Buckminster fullerenes, they have delocalized electrons, but only delocalized to within the molecule, which means they will not conduct electricity, okay? So these electrons move, and they give it some pretty special properties. Ideally, that the benzene ring is extremely stable and has similar chemical properties to alkanes, and we'll talk about those when we get to chemical reactions with them, right? Even though they are similar structurally to alkenes, okay? Because if you think about what happens here, or alkenes and alkynes, this formula for this benzene is C6H6. Okay, and that indicates that there's quite a few double bonds in there to remove some hydrogens, because a cyclohexane would be C6H12, right? That's just a normal cyclohexane. That's saturated, which means it can't have any more hydrogens onto it. But the C6H6 because you can't add any other hydrogens onto it, it's also in theory supposed to be saturated as well, right? But its formula looks more like a alkene or an alkyne with lots of double bonds in there, taking away its bonding capacity, right? But that's this benzene ring, extremely stable, and they're just a bit different to your normal cyclos, right? So when naming these, you just follow the rules of naming cyclic hydrocarbons for numbering. Okay, so effectively you go with whatever side group or functional group was there first, and you do not need to number the double bonds because technically there are no double bonds within this benzene, right? And then because they always have 6 carbons, you don't need to have a main chain name, and you just replace the word with benzene because, like, you know, main chain names are for things of different lengths, and benzene's only going to have one length. Okay, so you can also draw it like this. Oops, don't draw it with a highlighter. You can draw it like this. This is the preferred way to draw benzene rings. Okay, it's just the symbol that we use for benzene, where each of those vertices of the hexagon is a carbon. Right, so if I would draw this one here, this would be methylbenzene. Okay. When you draw it the other way, it's called the Kekuli structure, and it is technically not an ideal way of showing this structure, okay, because this one shows double and single bonds. It helps you understand how it works, but it's not really best representing the actual structure. So it's best to draw it like this if you have to draw the carbons in, okay, with a circle in the middle. All right, so this is bad, this is good. All right. But anyway, methylbenzene is there. Don't need to give it a number because there's only one side group. Okay, so let's go add some other stuff to it. Let's go add in something here and something here. Okay, so if these get numbering priorities, okay, these ones should have the lowest numbers. All right, so this is going to be one of the unusual cases where this is going to go 1, 2, 3, or it's going to go 1, 2, 3, right? And so you're going to decide whether it's going to be the yellow or the green. So the yellow or green, which one is going to be? It's going to be the yellow, because if you use the yellow, the methyl group will be on number 4. If you use the green, the methyl group will be on number 6, so it's not going to be very useful. All right, why can't you number it 1 over here, 2, 3, 4? All right, and then you get a 1, 2, and 4. Compared to having a 1, 3, 4, because the 1, 2, 4 is a lower combination than the 1, 3, 4. You should be numbering it so that the other bits and pieces get the lowest number, right? The halides get the lowest number. All right, so that's the idea there. So this would be what? 1, 3 dichloro, 4 methyl benzene. All right, let's draw another one. Okay. Okay, so you draw a hexagon. Now, please note, these 2 hexagons are different. Okay, you should ideally draw that one and not that one. You should draw them on their side because it's a little bit better. Okay. So boring with chlorines. Let's do something different. Let's put on a ethyl group over there. Something like that, and let's just draw something over here. Okay, how to number this the smallest? Then I would have it going 1, 2, 3, 4, 5, 6. Okay, if you number it the other way, the chlorine gets too high a number. Oh, actually still goes, yeah, the chlorine goes to number 5, which is not ideal. Okay, so this would be 4-chloro, 6-ethyl, 1,2-diodo-benzene. Okay, so that's how you name these benzene, and that is the end of our naming series. Okay, so now we're actually going to start seeing what they actually do. All right, adios.